My name is Gabriel Altman, and this is my final project here. It's the large wind turbine over there. So, why would I want to build a wind turbine? Well, I have a personal interest in renewable energy systems, and I also thought that building a wind turbine would be a very fun project. And I thought it would be a little more interesting than a solar project. No disrespect to my classmates who do solar projects, but let's go watch the solar panels charge, said no one ever. So I'm really proud of my project, and I've told a lot of my friends about it, and everybody always asks me, wow, you built a wind turbine. How much power does it produce? And I usually answer none. And people look at me and they're like, well, that doesn't make any sense. And I say, wind turbines don't actually produce power, they more collect power or intercept power out of the wind. So people will say, okay, well, how much power does your wind turbine intercept from the wind? And I say, it's a 10-foot wind turbine. And all the engineers here are going to say, 10 feet is not a unit of power, or a measurement of power. What do you mean that's how much power it produces? But 10 feet is actually a very good guide of the turbine's potential to intercept power. Let's see if I can get it to work. Very good. All right. So let's look at how much power is actually available in the wind to capture. So basic physics, we have a formula here which says that your power is equal to 1/2 rho AV cubed. And rho is the density of wind, A is the area of your turbine, and V cubed is the velocity of the wind. So if we look at this and we want to capture power out of the wind, we say, well, what can we influence out of this equation? Well, the density of air, can we influence that where our turbine is? A little bit, actually. There are some things we can do that'll affect the density. We could say, for example, put the turbine at high altitude. If you were to put this turbine in Denver, Colorado, it would only make about 85% as much power as it would make here in Florida. Also, humidity and barometric pressure will affect the density of the air, but there's not much to do about that. Area, we can definitely affect how much area is intercepted by making a larger rotor on our turbine. And velocity of the wind. Now, I might be a magician, but I can definitely control the velocity of the wind. So, the important takeaway from this is that if you double the diameter of your wind turbine, you'll actually get a 4 times increase in the amount of power you can intercept. But if you double the velocity of wind, you'll get 8 times as much power available to your wind turbine. So, as far as affecting the velocity of the wind, what can we do to change that? Well, the first thing we can do is we can put the turbine in a favorable location for high winds. So, for example, out in California in some of the mountain passes where there are large utility scale installations, they have terrific wind resources for making power. But if you can't move out to California and you're stuck in an eastern state, you can actually influence the velocity of the wind that your turbine experiences by changing the height of your turbine. So by putting your turbine on a taller tower, due to an effect called wind shear, your wind speed increases with the height of your turbine height. So let's look at how much power is actually available in the wind. So this is a curve for how much power a 10-foot diameter rotor can intercept. And because the velocity increases, or power increases with the cube of the velocity, we have a nice rapidly rising function here. So at 10 miles an hour, this 10-foot diameter turbine can intercept about 400 watts out of the wind. 20 miles an hour, we get up to about 3,200 watts, which is pretty good. 3,200 watts at 20 mile an hour winds. Now we're talking some power, right? Well, no, not exactly, unfortunately. Actually, I didn't even go. If we go up high at 40 miles per hour, all the way up to 25,600 watts, which is enough to power a house. But unfortunately, we don't actually get to keep all that power. There are, in so many places in life, there are losses and limits. So what kind of losses does our turbine experience? Well, right off the bat, we're going to lose about 20% to friction in the bearings and drag. We'll lose about 25% in the wiring of the system. We'll lose about 12% in our rectifier, and we'll lose about another 5% in our inverter. So, and the most important loss we have is the VETS limit, which is the absolute limit for the amount of power that any turbine rotor can intercept out of the air. So on a large commercial scale, utility scale turbine, they might be, say, losing 60% of the power. On a small scale turbine like this, probably closer to 70 to 80% will not be able to be collected. But even with the limits, we'd still have a pretty favorable curve. If we look at our chart here, it looks like at about 20 miles an hour, or 20 meters per second, we'd be close to 10,000 watts. Well, that's still pretty good, right? 10,000 watts? Not exactly, there are definitely limits. So the first limit we come up to is the heat dissipation potential of this alternator. And that kicks in around 2,500 watts. And if you try to have this thing sustain more than 2,500 watts for any given period of time, it will overheat and burst into flames, and that is a bad thing for your wind turbine. Definitely not anticipated behavior. The other area limit would be the structural strength of the turbine itself. In hurricane force winds, this thing will become matchsticks all over the landscape. It can't handle that. So the turbine actually needs a system to protect itself from those high winds. So it's protected by what's called a furling system. And the furling system, which I can't really demonstrate in here too effectively, it allows the rotor of the turbine to face away from the wind to reduce the area that's exposed to the wind. And it actually, I'll show you a little bit. The tail of the turbine is going to always stay facing into the wind through the large panels on the vane, but the rotor itself is actually on a hinged pivot and can hinge out of the wind separately from the tail. And the weight of the tail will return it to its original position when the force is dissipated. All right. Also, this turbine should start furling at about 20 mile an hour per winds. So, the turbine also has a parking brake, which is a magnetic brake, which sounds really, really high tech. It's actually not high tech at all. I have a little demonstration of a magnetic parking brake here. Might look like a bicycle wheel. It is actually a bicycle wheel. I need a volunteer. Who would like a volunteer? So if you turn this little knob here, say it takes much force to turn at all, not too much. Put our magnetic parking brake on there. Much harder, yeah. So when you short circuit the contacts on an alternator like this, a permanent magnet alternator, it becomes very, very difficult to turn. So you can actually apply this brake when this turbine needs service, or when you're installing it on a tower or moving it to control the blades. All right, so now that we're capturing power out of the wind, let's actually make some electricity. That's what this turbine is for. So generating electricity. The most fundamental thing about generating electricity is that if you expose a conductor, like a wire, to a changing magnetic field, it's going to induce a voltage. I have a little demonstrator over here if anybody wants to play with it afterwards or whatever. So if we look at this formula here, which approximates the voltage output of an alternating current generator, we have a formula which says that our electromagnetic force is equal to the number of turns of wire times the strength of the magnetic field and the area of the coil multiplied by the rotational speed. All right, some basic physics. Now that we've got that down, let's look at what we can affect out of this. So, let's see, N, the number of turns of wire in our coil, that we can definitely affect by winding larger coils. B, the strength of our magnetic field, we can definitely put more powerful magnets in it. A, the area, we can definitely change the shape of our coils, but omega, that's sort of regulated by the speed of the turbine. Not too much we can do with that. So let's actually talk a little bit about the alternator that this machine is connected. The first part of building the alternator is to actually wind up coils. Got a couple of spares over here. One of our coils out of the alternator. This was a test coil. It didn't have nearly enough turns to produce the voltage that my generator needed. But they were hand wound from big spools of magnet wire. We had a little magnet winding jig here that was powered by a drill. After the coils were wound, I arranged the coils on a little layout plate here to get the correct shape of the stator. All the coils were glued together with little bits of fiberglass, actually. You can see the little white squares there, just to hold them in place while I assembled the stator. This is the stator mold. The stator is the stationary part of the alternator. It was made out of plywood. It was cut by hand with jigsaws. I did the best I could to make it circular. The crevices were sealed with caulking to keep the resin from leaking out. And I placed all of the coils into the stator, soldered them together. It's wired in what's called a star or Y configuration. And then the next step was to actually cast the stator. So has anybody here actually built model airplanes as a kid? All right, so you know the smell of that glue?
Yeah.
We used a few drops of it. We used about 1.5 gallons of vinyl ester resin, and I was having a psychedelic experience. So this is what a finished stator would look like. This is not actually my machine, but my stator is a slightly smaller version of this. It looks like a big puck full of coils, and that one probably actually still smells a little bit like this. The magnet rotors that the permanent magnets are attached to, I don't have any good pictures of those, and that's because that was probably the most hazardous part of the construction of this machine, and the part that scared me the most. The magnets that I bought are extremely powerful. They could definitely cause great injury. So when I had all the magnets laid out on their steel plate, I was very careful not to have anything metallic nearby. I didn't even let anybody else go near them. So I don't actually have any pictures of the magnets, rotors, while they're assembled. But that is one of the magnet rotors as I was drilling it out and setting it up. After the alternator was mostly completed, I got to building the frame. This design can be built in a shop without any machine tools. You can build it all of things your average home shop would have. The steel is nothing exotic. Most of it is just Schedule 40 steel piping and mild steel like you can buy at the Home Depot. The only precision cut parts were the stator bracket and the magnet rotors, which you can come up later and look at. Those were cut on a water jet table for precision, but there are definitely some workarounds that you can do in a home shop with a field expedited drill press. After all the metal parts were cut, I got them all prepared for welding. There was a lot of sanding and a lot of grinding and not too many metal splinters. Did all the welding myself. That's not actually me welding. That's somebody else welding a different turbine, but that's one of my welds there. I was pretty pleased with my TIG welding. Came out pretty good. And then the blades. The blades are the area that I get the most questions about. And the reason that they look so good is that this is not the first blade that I've made, or the second, or the third, or even the sixth. So I went to a turbine building workshop where, as a class, we built a very large turbine. And then we built a very small turbine, and then everybody went home and left me on my own to build my turbine. And I was directed by some very fine woodworkers from the mountains of North Carolina who know a lot more about woodworking than I will ever know. And I received a lot of very good guidance. So the blades are made from cedar, which is a very inexpensive, very lightweight material. It's a very accessible technology to make blades out of wood. All you need are basically a draw knife and a power sander. And the construction techniques are probably something similar to what you would have seen in the aircraft industry in like the 1920s or 30s. So we started with laminated rough blanks of our blades. We just used a glue called Tight Bond and planed and glued all the surfaces together. We did rough cutting and shaping on a bandsaw. Then we did the layout. We laid out the profile of our airfoil on the well, that's great. All right, there we go, look at that. So we laid out the profile of the blades on the tip here. This is our airfoil shape. And the blades are actually twisted. It's tough to see, but there's actually, we scribed a line down the edge of the blade and down the leading edge. And we used a saw to cut a series of grooves in the wood. And then I used a draw knife for the next 3 days and filled garbage cans full of cedar shavings and got the blades roughly equivalent to their finished shape. And then afterwards came the power sanders, which I will tell you that sanding hides a lot of mistakes and a lot of errors in woodworking. And once the blades were finished, I packed up and came back here where I finished up final assembly. The tail vane was made out of 1/4-inch plywood, just cut by hand. And then the alternator was finished assembled in the shop here, and then it was time for some basic testing of the alternator. So I couldn't actually put my turbine on a tower because towers are very expensive. So the best I could do to test my alternator was to have my friends
in the shop, Sean, thank you very much. He built me a lovely plastic hub that I attached to my alternator, and I attached a bolt to it, and I attached a drill to spin my alternator, and promptly shredded the plastic hub. So I went back to Sean and said, Sean, I broke the hub. Can you make me another one? It's a rush job, I need it today. So he jumped right on it and made me a second hub, which I also destroyed. So the lesson is that plastic does not work very well. So option 3 is to go to your scrap steel pile and get a big chunk of steel and drill a couple of holes in it. There we go. Worked perfectly. No problem. I hooked our alternator outputs up to an oscilloscope, and my objective was to try to capture frequency and amplitude of the sine wave that my alternator produced. And the oscilloscope did a beautiful job capturing a lovely alternating current signal from my alternator. We actually have a 3-phase alternator. It's a little tough to see, but there are 3 different phases represented by 3 colors there. And the alternator the oscilloscope was able to capture this data and send it to Excel, where I was able to plot our much more complicated waveform, which didn't really help me to understand a lot about how my turbine was going to perform. But luckily, thanks to Google and some help from some mathematically oriented friends, I looked into what's called a fast Fourier transform, which will allow me to compare the frequency and the amplitude of my complex waveform at discrete segments here. So it doesn't really show up, unfortunately, in green and white, but if you could see it, you would see a very, very flat response here and then a very strong peak here. And what that peak represents is that at this specific frequency, I had an amplitude of my wave that was equivalent to this value of about 30 here. And I was able to analyze more of the wave and come up with a relationship. Very difficult to see with our light here, but you can see if you look from peak to peak to peak to peak, there's actually a very linear response here of frequency to amplitude. And so why do I want to know the frequency of my waveform? Well, that's because I can convert frequency into the rotational speed of my wind turbine. And after some math, it comes down to a very simple function that my rotational speed of my turbine is just 10 times the frequency. And the reason that you need to know that is because of the performance of the wing. If your alternator needs to spin at a certain speed to produce power, and it can't make that speed at low wind speeds, you're not going to be producing any power. So anyway, I plugged all of my frequencies and voltages into Excel, and there's a beautiful linear relationship between RPMs and voltage. And I discovered after plotting all this data out that I made a mistake and recorded this data with a significantly larger load on the alternator than it's designed to run with. So I need to repeat this measurement in the future. But it did let me estimate that my alternator should start producing power in wind speeds of 7 miles an hour. So very big amounts of power. My future plans for the project are to get it installed on a tower. This is a wind turbine. It's designed to produce electricity and not sit in my garage or a workshop, so I'd love to see it on a tower. Once I get it on a tower, I can collect a lot more data. I'd like to see if it performs as well as I expect it to. And I'd also like to look into making blades out of materials other than wood. It doesn't really make sense economically or performance-wise, but it would be a very, very good opportunity to learn about how to work with carbon fiber. Thanks for your patience, thanks for listening, and thanks very much to the faculty members and the staff here at Palm Beach State who have helped me through this program for the last 2 years. And if anybody has any questions, I would love to answer them. All right, 2 questions. Yes, sir.
Did you consider feathering the blades, changing the blade pitch instead of turn the whole?
Definitely. There was a very successful small wind generator called the Jacobs wind turbine. It was very popular in the 1920s and 30s for charging battery systems in farms for people to listen to the radio. It used a flyball governor so that as the rotational speed of the hub increased, the blades would actually feather themselves. Unfortunately, the machining required to build a reliable flyball governor was way beyond what I had access to. There was another company that made one that worked with like a torsional spring that accomplished the same effect, but also this turbine can be built without a lathe or a mill or any sort of gear cutting machines. But that would be a far more ideal solution. Yes, sir.
150 hours or so. Yes, sir.
In your research, how did you determine the number of blades? It seems like all wind turbines typically have 3 blades. Why is that so common?
Yeah, they do. Generally speaking, it tends to work very well as far as vibrations. It tends to limit the vibrations of the machine and keep them running more smoothly. 1 and 2 blade machines have been tried in the past and they haven't been terribly effective. Yes? Oh, yes ma'am.
I may have missed it, but were you actually able to test it with 7 miles an hour winds?
Only bench testing so far. I haven't been able to put it on the board yet. Yes, sir.
On your windings, if you just use the air core,
Yes.
if you would have used like iron core, would it help increase your power generation?
It would have allowed me to build an alternator that used a lot less copper and much weaker, less expensive magnets, but it would have also resulted in a lot more cogging and vibration of the machine when it's running. Also, the magnetic cores that they use on electric motors, the alloys they use that have really favorable hysteresis variables would be very expensive and hard to access. Yes, sir.
Maintenance, if you did need that put up in the air and functional, how long do you think it would be until it requires some maintenance?
So a wind turbine like this would turn about the equivalent of what a car would do for about 200,000 miles every year as far as the number of rotations. So annually, it should come down, half the blades re-oiled, half the bearings repacked, and
You may have mentioned, but at a certain speed, you're getting peak power out of it. How do you measure the speed? Is that when magnetic braking comes into effect?
The magnetic brake is more for maintenance and for service. The furling mechanism is really what we're limited. This turbine would require sort of a hands-on monitoring if you expected a very powerful storm to come through and very high winds. So, I mean, I wouldn't just rely on the furling to protect it with 100-mile-an-hour winds, but for day-to-day usage, it should furl. The hub is actually offset from the yaw axis, so the tail will stay facing into the wind and the hub will actually hinge in on itself and reduce the area exposed to the wind.
Great, that's great design.
The engineering genius, actually, the credit would go to a number of people. There's a gentleman in Scotland named Hugh Piggott, who's been living off-grid since the 70s. He and a number of other enthusiasts for small wind out in Colorado have been refining this design for about 40 years. So I wanted to start with something that had a very high chance of success. There's a very active internet forum dedicated to folks who are interested in small wind, and the forums are littered with pictures of burnt, twisted, and broken turbines. So this represents a lot of lessons other people were generous enough to learn on my behalf. Sir?
The system resonant frequency is highly dependent on the blade design. How did you come up with your blade design? Is it something that was very predefined for you?
This is a blade design that other engineers came up with. The aeronautical engineering for blade design is well beyond my level of education at this point. But if you know anybody at the College of Aerospace Engineering at the University of Florida, I'd love to learn more about it. All right, well, thank you very much.